Welcome back to another video with us here at LMD and STEM Academy. In this video, we will be working through the June 2013 Unit 2, Paper 2, and it's question 5, and it's about solvent extraction. So 5 part A says define the term partition coefficient, right? So partition coefficient is an equilibrium constant which represents the concentration of a solute in the organic phase divided by its concentration in the aqueous phase. And so we can represent this equilibrium as such, where we have X representing our solute in the aqueous phase being equilibrated with X in the organic phase. So there's an equilibrium that gets set up, right, whenever we do a solvent extraction. And so from a mathematical standpoint, the partition coefficient, or also written for short as KD, is equal to the concentration of your product. So that's your solute in the organic phase divided by the concentration of your solute in the aqueous phase, right? And so this is how we can represent partition coefficient mathematically. And if I were to do a quick sketch of just how we can visualize what's going on, right? Imagine I have my separatory funnel where I did my shaking and I allowed the solutions to equilibrate. You can imagine that when all is said and done, when everything has been equilibrated, right? I would have two layers, right? I'm gonna have my organic layer, right? Being the one that's on top. And I'll have an aqueous layer down here on the bottom. And so you can imagine that my solute, I'm gonna have some of my solute in here, and I'm gonna have some in here. So it's partitioned between both of these phases, the organic phase and the aqueous phase. And so we represent that using this expression here, known as the partition coefficient. Okay? All right, so we're gonna move forward now. And so we're gonna go to part B now. B says that when butane acid was shaken with a mixture of water and ether, 10 centimeter cube of water was found to contain 0.854 grams of the acid, while a similar volume of ether contained 0.159 grams. In a separate experiment, 10 centimeter cube of water and 20 centimeter cube of ether were shaken together with 1 gram of the acid. And we're being asked to calculate the mass of the acid found in the aqueous layer. Okay, so here's our strategy. The first thing that we have to do is we're gonna have to start by finding the partition coefficient, or the KD value. We're not given it here, and sometimes, in most cases, you'll be given the KD, but if you're not given it, then you have a means of calculating it based on the information that they've provided, and that's the case here. So we're gonna start by finding the partition coefficient, or the KD, and the KD, as we said earlier, is gonna be the concentration of the solute in the organic phase divided by the concentration of the solute in the aqueous phase. Now, in this case, butane dioic acid is our solute, so that's our X, right? So that's our X. Our aqueous solvent is water, right? And our organic solvent is ether, right? All right, and so initially, we're shaking 10 centimeter cube of water with 10 centimeter cube of ether, because it's an equal volume of ether. And when we did that, we found that this mass of the butane dioic acid was found in the ether layer, and then 0.854 grams of the acid was found in the water layer. And so just to do my little sketch that I did just a while ago, I'm gonna sketch here again my separatory funnel after everything has equilibrated, right? So here's my separatory funnel, right? So that's my separatory funnel. And here are my two layers, right? So this, the lower layer, is our aqueous layer, right? Because water is going to be more dense than the organic solvent, which is ether. So my organic layer will be on top always, and my aqueous layer will be on the bottom. So what we're saying now is that both of these were equal in volume. So the organic layer had a volume of 10 centimeter cube. So it was 10 centimeter cube of my ether, and it was 10 centimeter cube of my water, right? So that's what we had there in this initial case here. And what we found was that in here, there was 0.8. Well, actually, that's my aqueous layer. In my aqueous layer, in my organic layer, which is the top layer I'm focusing on now, it was 0.159 grams of the acid. And then in the aqueous layer, that's where we had 0.854 grams, okay, in that 10 centimeter. And so right now we have a partition that got set up there, right, between my aqueous layer and my organic layer. And I have the concentrations because I know mass and I know volume. So I can just plug those numbers in here and I'll be able to come up with my KD value. So let's see how that calculation proceeds, right? So here it is, right? Let me just move up my picture so you can see the numbers there. So let's just shift this photo up, right? So here it is now. In my organic layer, I have 0.159 grams in 10 centimeter cubes. So that's a mass concentration at equilibrium for my organic layer. And I'm going to divide that by the mass concentration in my aqueous layer, which is 0.854 grams in the 10 cm cube. And when I work that through, I come out with a partition coefficient of 0.186. Okay. So now that we have our partition coefficient, we can proceed further now to ultimately find the mass of acid found in the aqueous layer. Because what we're doing then, right, in the separate experiment, what's happening is that now, right, we're changing these variables, we're changing these numbers. So in the separate experiment now, what happened was that we had 10 centimeter cube of water. So my aqueous layer now had a volume of 10 centimeter cube. And my organic layer now had a volume of 20 cm cube, because that's 20 cm cube of ether, right? And we're shaking. We're putting in 1 gram of the butane dioic acid in here. Okay, and we're shaking. And it's going to get partitioned, right? That 1 gram is going to get partitioned between both layers. So just keep that in mind. Our total mass that we're putting in is 1 gram, and we're shaking it with ether and water, and it's going to get partitioned between both layers. What we want to find is to find out what mass of the acid ended up in the aqueous layer. So now I'm going to find out how much M, right, was in 10 centimeter cube. And then if my total was 1 gram and M ended up in my aqueous layer in that 10 centimeter cube and my total was 1, then the amount that's going to end up in my organic layer is going to be my total minus how much went into the aqueous layer. So I'm going to have 1 minus M, that's my mass, that's going to be in the 20 cm cube. So let me repeat that again. If M, let M represent the amount that went into my aqueous phase. That's what we're trying to find. If M went into my aqueous phase and I started with 1 gram, then in my organic phase, I'm going to have the 1 gram minus the M, whatever went into the aqueous phase. So that's our new equilibrium that gets set up when we're shaking in this separate experiment that we're doing here. And so what we have to do now, all right, so let's proceed forward. Here, I'm saying I'm letting M be the mass of acid found in the aqueous layer, which you can see in my picture here. So now what we're going to do is we're going to set up, right? We're gonna find our new equilibrium concentrations for the solute in the organic phase and the solute in the aqueous phase using these numbers, these unknown variables here, and the known volumes. So then this is what we're going to have. Right, we had our KD from up here. It still carries forward. It's not going to change. It's an equilibrium constant. So assuming our temperature remains the same, this will hold true again, even in our separate experiment, right? So that's still true. My KD is still true. And now in my organic phase, my concentration will be the mass divided by the volume of the organic phase. So that's what we have up here, for my organic phase, 1 minus m over 20. And in my aqueous phase, I'm going to have m, right? M is the mass in there and the volume is 10. So my mass concentration is now m divided by 10. Now, remember, we're trying to find the mass of acid in the aqueous layer. So we're solving for m, right? And so when I do this in my calculator and I solve for m, I come up with a value of m being equal to 0.728 grams. And so that's the amount of mass of the acid that will be found in the aqueous layer. Okay? All right. And so with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on the left here, you'll see the next video up. And if you look on the right here, you'll find our Module 2 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So, thanks for watching, and we'll see you in our next video.